We are now going to look at Appendix 3.5, Proof by Resolution. So before we talk about this different proof or alternative proof method, we need a couple of definitions. So the first definition is a definition of what a literal is. There are certain types of well-formed formula or variables that stand for a well-formed formula as follows. So any atomic formula is defined to be a literal, as well as any negation of an atomic formula. And then, as I mentioned before, formula variables are also literals, or any of their negations are literals. So for example, P is an atomic formula, so it's defined to be a literal. Not P is the negation of an atomic formula, so also a literal. Not bottom is also the negation of an atomic formula. We could also include QR, not Q, not R, and top and not top. And then formula variables are A, B, C, any capital letters, and their negation, so not B, and so on. And then the next definition is the definition of a clause, and this is defined to be a disjunction of literals. And you may know that disjunction simply means separated by or. So essentially what we're looking at is different formulae or formula variables that represent well-formed formulae in which the only connectives that they include are or and not. So examples of clauses, P or not P, right? The only connectives here are or and not. And not top or A or not B is another example of a clause. The only connectives we have are ors and nots. And the reason that we need these two definitions is simply because we're going to be interested in looking at well-formed formula which only have the connectives or and not. You may recall that, in fact, these are the only two connectives we actually need to represent any well-formed formula. We have equivalent well-formed formulae or equivalences in which we can represent any other connective in some way using just or and not. And so this is what the proof by resolution, one of the goals is simply to transform every well-formed formula in a theorem schema into a clause, so to have only the connectives or not. And then we want to apply the cut rule to be able to cancel various variables to be able to conclude simply bottom. So you'll see how this works. And this is what we're going to go through in this video. So we're going to look at this proof by resolution mode. And so, as I mentioned before, we want to transform any well-formed formulae in the theorem schema to be clauses, so to contain only or and not as their connectives, and then apply the cut rule as many times as we need to simply conclude bottom. So how is it that we are going to do this? So always the first step is to actually take whatever it is we're trying to prove and move it to an assumption. So using deduction and proof by contradiction, we want to move everything to the assumption side of the proof symbol, and we want to have only bottom on the conclusion side, right? You may remember that the cut rule allows us to cancel out a variable and its negation and be able to conclude not in the end. So deduction and proof by contradiction allow us to do that. So you may recall, right, here's the top one is deduction theorem and the bottom one is proof by contradiction. You can ignore this statement. What is really important about knowing about the deduction theorem is simply that if we want to prove an implication, A implies B, what we can do is take this assumption as an assumption over to the other side. So that's what we want to do. So whenever we're looking to prove an implication, proof by resolution, the first step we do is move any hypotheses in the implication to our hypotheses of the theorem that we're trying to prove. So we get rid of as many arrows as we can by moving the assumptions, the well-formed formula preceding the arrows, over to the other side. And that simply tells us that we want to prove B. Once we have removed all of the arrows, we're left with some well-formed formula we're trying to prove. And remember from the last video, proof by contradiction says when we're trying to prove a theorem, we can actually assume the negation. So take the negation of what we're trying to prove and assume that. So move it over to the other side and derive a contradiction. So to derive bottom. So this is how we move all of our well-formed formula that we're trying to prove to the assumption side and have only bottom on the conclusion side. So the first two steps are to apply deduction theorem as many times as we can, if we can. If we have any arrow, then we can apply the deduction theorem. And then we apply proof by contradiction to move whatever is remaining over to the other side with the negation, and we're left with bottom on the other side. Okay, so let's look at a particular example to see if this becomes clear in a particular example. So suppose we have a series of assumptions. This is our set gamma of some well-formed formula, and we're asked to prove simply the implication A implies B. So by the deduction theorem, we know that it suffices to move A to our hypotheses and simply prove B. So that allows us to move one part of the well-formed formula to the assumption side. Okay, so there's how we moved A. Now, here we have simply that we're trying to prove B, so by proof by contradiction, we can take the negation of B into our assumptions and replace that with bottom. So this is the statement we would be asked to prove. So we have a series of hypotheses in gamma, plus we have A and not B. So now we want to look at all of these assumptions. And the next step is to ensure that all of these assumptions contain only connectives or and not. So, for example, if one of our assumptions involves the equivalence, we can apply the ping-pong theorem to translate that equivalence to a different statement. So we know that A equivalent to B, so the well-formed formula A equivalent to B, so some well-formed formula with equivalence in it, is the same as A implies B and B implies A. Okay, so we would replace any A equivalent to B statement with this one. So we will still have to do more to apply to these theorems in order to be able to get only or not. So we need to see how to get rid of and how to get rid of any implications, new implications that we add. So let's look first at the implication. So recall, we know that A implies B is equivalent to not A or B. So this implication theorem allows us to get exactly what we need. So in one step, we can drop the arrows and get a clause, one that has only connectives or not. So that allows us to get to a well-formed formula we're looking for. So now let's consider and. So in some cases, we may have an and connected by the negation. So if we're taking the negation of A and B, by De Morgan's law, we know that we can distribute this negation through and change the sign. So now we do have not A or not B, so a clause which only has connectives or a not. So that takes care of that if our and is negated. Notice that this one actually already is a clause because the only connectives it has is or not. But sometimes it's helpful to make it a little bit simpler. So we could apply De Morgan's law to this to distribute the not through and get an and. Now notice we have this and here, but we'll see in a little bit how to remove that and altogether, and also is really helpful. So, but before we can do that, we want to consider the case where we're distributing or over and, right? So this one connective is preventing us from being able to separate the two out, but by distributing or over and, we get two clauses connected by an and you may remember the split rule allows us to simply separate any well-formed formula with and into two separate well-formed formula. So whenever you see A and B, for example, you can write A, B separately. So this allows us to drop and altogether. And then finally, here is the cut rule, right? So for example, if we have two well-formed formula with a variable and its negation included in there, separated by ORs, then that simply allows us, the cut rule simply allows us to drop or cancel out A with not A, and we're left with what's left, B or C. And the idea is that we simply want to cancel as many formulas as we can until we get to this case, where we just have a formula and its negation, and then the cut rule allows us to prove bottom, which is what we are trying to do. So we'll see in class a number of different ways to apply the proof by resolution to prove theorems. And you'll, I think, really like this method of proof because it has step-by-step process that you need to go through, right? You know exactly what you need to do. Move all of the assumptions over, move all of the well-formed formulae on this side, so on the proving side of the proof symbol, to the assumption side by applying the deduction theorem and proof by contradiction. And then we look at our assumptions and we transform them into statements that look like this, with or and not, by applying the ping-pong rule if we have any equivalences, the implication rule if we have any arrows, De Morgan's law if we are negating and or, distributivity of or over and to be able to separate, splitting to be able to cancel the ands altogether, and that will allow us to get only well-formed formula with ors and nots, and then we can apply the cut rule as many times as we need to conclude bottom. And that's the end of the story.